Hello YouTubers and fellow hams. Well, it's been a cold couple of days here in northern Indiana. It was barely up in the 50s yesterday and it was 43 this morning. So being that I was kind of trapped in the house and didn't have a lot to do yesterday, I spent the day experimenting with magnetic loops. I love building magnetic loops. They're so easy to build. In fact, yesterday I built 2 from scratch and I rebuilt 1. So I've got a little bit of information for you today from my experiments, and hopefully you'll find it useful. I was thinking about the radiation pattern over a magnetic loop. Now, in general, a circular loop has a circular radiation pattern, right? It's like a donut. It just goes out in all directions in a horizontal plane. And then there's a null perpendicular to the loop. So it looks like a donut. It's like the radiation pattern of a vertical antenna if you put it on its side. I was trying to think of ways to pull that pattern out. You know, get more of the energy going outwards and less of it going up and less of it going down. And so I started playing with geometry. Now my first idea was a squashed magnetic loop. Taking the round loop and squishing it down a bit. You know, not quite oval, but yeah, kind of oval. And my thinking was that perhaps the radiation pattern would follow the geometry. Now, there were 2 things that I observed in testing the squashed loop. Unfortunately, I didn't take a picture of it, but I did take a picture of the next one. We'll get to that. Taking my field strength meter and going around the perimeter of the loop, keeping the pickup from the meter about 1 foot away from the radiator, there was indeed a much stronger accented outward field. It was very strong out here, and it fell right off up top, and it fell right off down below. So the geometry change did indeed affect the radiation pattern. The downside was, as soon as I took that circular symmetrical loop, which was symmetrical, you know, this way and that way, as soon as I made it asymmetrical by squishing it out, so it was wider than it was tall, the SWR went through the roof. I could not tune it down below 3:1 SWR, so it was pretty much useless. But it did exhibit what I had hoped, which was that drawn out radiation pattern. So I tried another pull on the geometry. I'd built square loops before, and they worked pretty well, as long as they were symmetrically square. So I did take a picture of this one. And what that is that's kind of like stretching the square up and squeezing it in on the sides. My wondering was if the longer legs on the sides, being a greater surface area, would cause that pattern to strengthen out to the sides. And again, that's what I observed. The pattern, the field on the field strength meter was much stronger, almost straight out to the side, and it fell off up here and it fell off down there. But again, the same problem that I saw with the squash loop, where I could not get the SWR down. It was terrible, so it was pretty much useless. Yeah, so geometry changes I don't think are going to work. Those loops really like to be symmetrical, horizontally and vertically. So my third experiment, I retooled my small 1 foot square magnetic loop. I wanted to try a tuning methodology that I thought would make it much easier to tune manually, and it did, big time. And also I made another observation on the field. So let's go look at the 1 foot loop, and I'll show you what I changed, and I'll show you how it behaves now. So this is my junk box 1 foot small magnetic loop. It's 1 foot square. Originally, I wanted to see how small I could make a magnetic loop and still get on 40 meters. And I just used junk that I had laying around in the basement. Now, what I did originally, there are 2 ways to lower the frequency of a tuned circuit. And a magnetic loop is basically a tuned circuit. You have a coil around the outside and a capacitor that's in series with that coil. So if you look at that electrically in a schematic, it's a tuned circuit. And there are two ways to increase or lower the frequency of a tuned circuit. One is to increase the size of the inductor, or the number of turns. The other is to increase the size of the capacitor. Now, originally, in this junk box loop, I went for increasing the inductor. And what I didn't have any copper to play with at the time as far as pipe goes, so what I did was I took some Ethernet cable, which is an 8-conductor cable, and I joined all the conductors together electrically so that it was basically equivalent to about a 10-gauge or maybe 12-gauge piece of wire. And then I ran it around the outside twice. So I had 2 turns around the outside of the loop. And I had a smaller capacitor for tuning. And that worked. I was able to get it down to 40 meters. It worked well enough that I could make contacts on it, but the trade-off was radiation efficiency. In a magnetic loop, the electrical resistance of that outer loop is critical. As little as 1/10 of an ohm of resistance will reduce your radiation efficiency a lot. So they almost always use big copper on the outside of the loop and big straps to the capacitor and good connections there. You want absolutely lowest DC resistance possible. So having 2 turns around the outside increased that resistance enough to bring down the radiation efficiency. The other thing that it did was it increased the voltage across the capacitor. And when you think about that, that makes sense. 2 turns of that inductor is going to double the voltage that it's inducing at the capacitor. And in fact, the small cap that I was using had plates that were close enough that I could get an arc across the plates at about 20 watts of power. On the 2-turn loop, that same capacitor, I could barely get to 5 watts of power, QRP from the 817, and it would occasionally arc. So 2 turns radically increase the voltage across the capacitor, which is a bad thing. So I retooled the loop yesterday. I changed this. I joined these 2 together down here so that they were basically 1 turn. Okay, 2 wires, but I connected them together at this side and at this side, so they were 1 turn around the loop. And then to actually reduce the resistance even more, I took this coax and I joined its center and shield together and added it to the bunch too. So I've got a lot of copper going around the outside to lower the resistance around the loop. And then I used a bigger capacitor. Now I got this at a Hamfest, and it's got pretty good plate spacing. Let me zoom in on it. Okay, I got this capacitor at a Hamfest for $5, I think. There's always some guy at a Hamfest that has a box full of capacitors. So this one is pretty broad ranged. It goes from about 30 picofarads when the plates are open to 500 picofarads when the plates are fully meshed. So that's a lot of capacitance. And it worked. With this capacitor and my 1-foot square loop, I easily get down to 40 meters. And when these plates are fully unmeshed, it's resonating at about 30.1 megahertz. So 40 meters through 10 meters with this capacitor. The downside to such a broad range capacitor is that tuning gets really, really, really sensitive. I mean, you can get to where you can't even see it move, but you can hear you go past the sweet spot on the radio. It's that sensitive. So that is the next change that I made to the loop design, and that is a fine-tuning capacitor. Now this came out of an old tabletop GE AM/FM tube-based radio from, I think, the 60s, maybe late 50s. Those early AM/FM radios, AM/FM, they have to have the FM section, had 2 variable capacitors in them. They had a dense one on the AM side, but inside of a separate enclosure they had a much, much smaller one for the FM VFO. And as you can see, this one does not have very many plates in any of the gangs. In fact, altogether, if these are paralleled, this thing is only from about 1 to 32 picofarads. So only about 30 picofarads of range over the entire rotation. So what I've done is I've paralleled this with the big cap. Okay, I've got the Yaesu presently front antenna, there we go. Now it's hooked up to the small magnetic loop here. And hopefully you can hear that. That's 20 meters. Let me make sure the preamp is off. Yep. Okay, I'm going to go over to the loop. I'm going to turn the radio up so hopefully the microphone is picking it up. And we're going to tune the loop. Now I put this capacitor about halfway, so I've got the most range to work with, and we'll tune the big capacitor until we hear the static peak. Hear that? And as you can see, I can move through the sweet spot and you can hardly see the cap turning at all. It's extremely sensitive. So I get it close with that, then I reach over to this one, and as you can see, I can move that quite a ways to go through the sweet spot. So fine tuning is super simple. I just, right there. Okay, right there I'm tuned. And if I come over to the Yaesu and I transmit, yeah, SWR is zilch. Let me switch this over so I can, yeah. Okay, SWR is basically 0. Now, if we go and we look at the loop again, in the center of the loop, I have an embedded field strength meter that is indicating the RF field around it coming from the loop. I use that for fine tuning. You've seen that methodology on my my big magnetic loop remote control box. So I'm going to zoom in on that meter, and I'm going to key down the radio. Got to kind of stretch across the room here. Okay, you can see that meter swinging up. Now, if I tune the big or the small capacitor, I'm turning it. Okay, I'm going to turn it a full inch. There, I turned it a full inch. You can see that that adjustment is very broad with that small cap. I can very easily fine tune the loop. So that was my my big change on this little 1 foot loop. Now, as far as sensitivity goes, increasing the conductor around the outer edge has increased its efficiency quite a bit. It still is not competing with the big 3 foot diameter loop back there, but it is usable. Easily usable on digital modes and even CW or sideband. Signals, yesterday when 40 was open, I was monitoring and switching between my external end-fed 98 foot wire and this little loop sitting here inside. And a signal that was S8 on the external wire dropped down to about S6, S5, S6 on the internal loop. So yeah, not as efficient as the external wire, but still usable. I did make a contact on it yesterday on PSK on 40 meters. The further up in frequency you go, the physical size of the loop is more favorable. Up in 17 meters and 15 meters, especially 15 meters, I started to not see much of a difference at all between the external antenna and this little loop as far as strength of received signals goes. So I'm going to do some QSOs on it and film it, and I might do a follow-up video just on-air tests with the retooled 1 foot loop. One final thing that I wanted to talk about in geometry of the loops, and I think, I don't know exactly why this is, but there is definitely something to it. I had a conversation, short chat conversation with a guy who was complaining that I always put my capacitors at the bottom of the loop and the coupling coil at the top, and he was saying that most of the RF radiation comes off the bottom of the loop, or comes off the capacitor side of the loop. I don't see that. Especially in the case of this one, I see much more radiation coming off near the coupling coil. Now, I don't know if part of that is because of, since I've rotated this on the corner, right, and I've got the coupling coil up here near the corner, the coupling band here and here are much closer physically to the metal of the outer loop. In other configurations, they've had the capacitor on the flat side of a square loop and the coupling coil up here in the middle, like there. And doing that, you've only got close proximity of this wire to that wire, and not from the sides. On mine, with this being up in the corner, I've got close proximity here and here, and I think that that helps things. But what I certainly see, in fact, let me rig up, get Whisper going, and I'll grab the field strength meter and I'll show you exactly what I see. All right, the loop is presently broadcasting a Whisper signal. Now, hopefully you can see this when I, okay. I don't know if you'll be able to see this with the meter. I might have to handy cam this. Okay, down here near the capacitor side of the loop, I'm getting, if I keep the antenna about 8 inches away from the conductor, field strength meter is about 1/4. As I move up, you can see it's going up, 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 almost full scale. Trying to keep this in the shot. Now it's full scale. Over the top of the loop, it starts to drop off up near the top. Now here's the interesting thing that happens. As I move around this side of the loop, it drops off again. We've got low radiation down here, and there it's almost nothing at that corner. And then it comes back up, down towards the bottom, but still not as far. So by far, the strongest amount of radiation off of this loop is in this direction. And I don't know why the radiation is asymmetrical. I would have thought it would be symmetrical in this direction, but it's not strongest at the capacitor. It's strongest up here near the coupling loop. And I've seen that even on my big 3-foot loop, radiation is always stronger near the coupling loop. Now, the gentleman had theories that as to why it should be the opposite. I've always seen it this way. So I build my coupling coils near the top of the loop because I don't want to push most of my RF down into the ground. I want to push it up into the atmosphere. And in this case, it looks like most of the radiation is up at this angle, out, you know, like this. And I've indeed seen with experimenting with rotating the loop around during Whisper broadcasts that my footprint follows that direction mostly. So for some reason, this little loop is even more directional than the big symmetrical round loops. I don't know why, but it's really interesting to me, and that's actually kind of useful. I've got almost a beam here. The RF coming out of this side of the loop over here is less than half what I'm getting out of this side over here. And the direction of radiation appears to be like that. So that's pretty good, you know, for DX. It's lower. It's still going upwards somewhat. So it's going to, you know, it's going to get out there and it's going to bounce off the ionosphere and come back down. Yeah, I don't know why it's more directional in that direction on this construction. So maybe somebody else can analyze that and come up with a theory. I'm going to continue to do some more reading, but something about having this close proximity on both sides of this, I think, makes a difference. And for whatever reason, it wants to go that way. So that's the retooled version of the junk box loop. The big innovation here is the fine tuning. If you're building a magnetic loop and you're going to do manual tuning, get one of these tiny capacitors out of an old AM/FM tube radio, or find one at a Hamfest or whatever. Get a really tiny variable cap with good plate spacing, which most of those little ones do have, and make yourself a fine-tuning parallel to your big capacitor for your loop. That way you can use a big capacitor to get a broader frequency range and still have fine-tuning control to easily tune the loop. So that's what I did yesterday. Thanks for watching. If you enjoyed the video, don't forget to give it a thumbs up. Also, if you're not already a subscriber, click to subscribe. Join us on the Facebook channel for discussion about the videos. And if you'd like to help support this channel, please click to support me on my Patreon page.